Minister of Culture and Innovation of Hungary, Mr. János Csak, dear Professor Ferenc Krausz, Nobel Prize laureate in Physics 2023, dear panelists, distinguished guests. It's a great honor to welcome you at the Red German residence here in Stockholm this afternoon. I would first and foremost like to thank my colleagues, Hungarian Ambassador Adrian Müller and the Austrian Ambassador Doris Danla, for making this happen, because actually we sat together over a nice coffee at the Hungarian residence, thinking of how this afternoon could look like, and the idea of a panel was born. And so it is wonderful that you immediately agreed to come and to speak to us here at the residence about your research, but also about your current work at the Max Planck Institute and the Ludwig Maximilian University in Munich. So you and your team have succeeded, we heard that before, in generating and measuring attosecond light pulses and using them in the first real-time observation of electronic movements. So electrons are small and very fast, and their movement has been considered unmeasurable since their discovery. So your basic research is now being used in medical diagnostics for the early detection of diseases. So all this is fascinating, and I think we are very excited to learn more about it in the coming hour. So it was your wish, Professor Krausz, to sit on this panel with your colleagues, Professor Kienberger, Professor Yakovlev, and Dr. Hentschel, and to discuss your groundbreaking discoveries. In doing so, you emphasize that science works best when knowledge is brought together. So international cooperation between researchers is key to tackling the challenges of our time. So without further ado, we look forward to the panel discussion, and I will now hand over to the moderator of this afternoon's event, Dr. Eureka Moment. So thank you again for being here this afternoon, and enjoy the panel discussion. Thank you.
Thank you very much, Ambassador. So welcome to you all. Welcome to the panel and to the audience, and also those following us online. So I'm the Secretary General of Public and Science in Sweden, which is an organization working to create dialogue and exchange between scientists and the surrounding society. So I'm thrilled and honored to be here today, moderating this discussion on this year's Nobel Prize in Physics and on the importance of international collaboration in science, which is, of course, a theme that was close to Alfred Nobel's heart as well. And moderating this with this very illustrious panel, I must say, starting, of course, with this year's Nobel laureate in physics, Professor Ferenc Krausz. So first of all, I'd like to congratulate you warmly on behalf, I am sure, of the whole audience to this year's Nobel Prize. And a warm welcome to Stockholm.
Thank you. And first and foremost, I thank Your Excellency, Ambassador Reinhard, for hosting us. It's great to be here. Thank you.
So what does it feel like to be in Stockholm?
Wow, good question. Well, I try to realize it, but there is little time for actually contemplating, right? That's the program is extremely packed, and therefore I think this can probably be processed and digested only when some more quiet time is coming up, maybe during Christmas time.
What were your feelings when you got the phone call?
Yeah, that's a good question. So that the first feeling was also, is this a joke, or am I still basically asleep and maybe I'm just dreaming? And so yeah, it was undescribable, I would say. Yeah.
Did it take you totally by surprise?
Totally. Not last, because we just had weeks before a Nobel Symposium, which the Nobel Foundation usually organizes to explore which field might potentially perhaps be suitable and who could be the candidates, but typically, if at all, an actual award prize comes up maybe years, many years after that. So this was completely kind of excluded in my thinking that this could possibly happen this year. And correspondingly, I was sitting in my pajama and working on my laptop. So that's, I think, the best proof.
And you've invited to join you on this panel and to participate in the celebration here in Stockholm 3 colleagues of yours. Dr. Michael Hentschel, who's now at the Austrian Institute of Technology. Warm welcome to you as well. Professor Reinhard Kienberger at the Technical University of Munich. And Professor Vladislav Yakovlev at the Max Planck Institute of Quantum Optics in Garching in Germany, and also at the Ludwig Maximilian University of Munich. Well, welcome to all of you. Were you less surprised when you learned about this year's Nobel Prize than the laureate himself?
No, I was equally surprised, I think. So actually, Professor Kienberger phoned me up one day and asked me, as it was in the morning, and he asked me, well, did you read the news today? And I said, no. And so he told me, yeah, Ferenc got the Nobel Prize. And yeah, I was surprised, especially, I mean, 5 years ago, I think, there was the Nobel Prize for Chirp pulse amplification, which is also in the field of laser physics, ultra-short laser physics. And so I found it quite astonishing that such a short time afterwards, again, a Nobel Prize in short time physics was awarded. So seems really to be something special.
Shows the importance of the field, doesn't it?
Yeah,
would you like to comment?
I would say I was not surprised but about the when. So I mean we've been joking a lot in the past that Ferenc will once get the Nobel Prize. So it was not really a big surprise that he got it. But as my colleague Dr. Hentschel said, I did not expect it for this year. So in the end, so I got an SMS from a colleague of mine just by congratulations, and I said, what for? and then he said, well, your former boss got the Nobel Prize, and I said, wow, cool. And then I made the phone call to my colleague.
Spread the news.
Yeah.
And Professor Yakovlev.
Same for me. I did not expect it, but of course, attosecond science was something very new and very significant, and it's not a surprise that eventually the field got the prize. But on that day, I had zero expectation that would happen.
I think we just got a lovely illustration of how each Nobel Prize in the sciences actually goes to a whole field and to a great group of colleagues as well, to experience your joy and joint surprise at this Nobel Prize. But I think we should start with learning something more about the actual research behind the prize. So I'd like to ask you, Professor Krausz, if you could start now with this audience of non-physicists, at least partly, to give us an explanation about what was your breakthrough about.
Yeah, thank you. Well, the word attosecond is around since the 3rd of October, and is put very much in the foreground. But actually, the attosecond pulses that appear in the first line of the citation are only a mean to an end. The actual end are not the attosecond pulses, the generation and the measurement, but actually it's something completely different. It is capturing the motion of electrons. This was the goal, and it was obvious that for achieving that goal, we need to generate or need to create a camera with a correspondingly short, sufficiently short exposure time. And these are the attosecond pulses. But why is it? Why we believe that electrons are important and their motion are important? That I would perhaps just very briefly put in a perhaps somewhat simplified way, in a following way. Actually, we all are made of electrons mainly. Right? Although our mass and weight is dominated by nuclei in our body, but they are not doing anything much. I mean, nuclei are doing something in nuclear reactors, right? But not in our body. Whatever is happening in our body, all sorts of biological, chemical processes, this is all the work of electrons. And obviously, if we want to understand how we function, how diseases are emerging, we want to understand this at the most fundamental level, then we just need to understand how electrons move. The same argument could be put forward in the context of technical gadgets. They are all also made up of electrons. Of course, their weight is determined by the nuclei again, but the nuclei are not doing anything in those gadgets. It's again the electrons. And it's not just electronics, it's also the quantum dots, which was the subject of the chemistry Nobel Prize this year. The same applies.
So I think just to help the audience grasp what an attosecond is, it's a billionth of a second. And I've been told that it relates to a heartbeat, like a heartbeat relates to the age of the universe. Is that correct?
Within an order of magnitude, I guess. But there is so many orders of magnitudes that's a good accuracy. But what I actually like more actually is to use here the speed of the electronics as a reference, because this is something that we somehow, it's still extremely fast, right? How electric current is switched on and off in the contemporary chips, but there we somehow still have a connection, and that's kind of a few billion times per second. That's electric current is switched on and off, and that's why our electric gadgets are so powerful. And this is kind of the sub-nanosecond scale, somewhat shorter a nanosecond. And now an attosecond is a nanosecond. So basically we are that much shorter than the electronics. Then the electronics is faster than our heartbeat.
So another way of talking about these orders of...
In 2 steps. You did it in 1 step.
So it's all about actually being able to take snapshots of the electron, and the electron speed is so fast because they're such tiny particles, but they determine everything from how electronics works to how biological system works. So it's really a key to understanding matter, be it biological or electronic. So is that?
That's right. Yeah. That's right. But if you allow me, this snapshot actually is a bit sort of cheating, because this might create the impression that we indeed take photographs. Unfortunately, we are not there yet. We are not really taking photos of where the electron is within the atom or the molecule. Maybe this will be possible one day with attosecond hard X-ray flashes of light, but we are not there yet. Right now we are just measuring some physical observables as a function of the exact moment when we take the snapshot. And the actual developer of the film are theorists. In our case, our chief theorist, Professor Yakovlev, who actually models the process that we look at, and with his modeling calculates how those physical observables that we can measure with our measuring instrument as a function of time, how those are supposed to behave. And if the behavior is the same as we see, then he can develop the film. And we can tell us, okay, at this moment the electron is this state, slightly later, 100 attosecond later in this state, and so on. So the theorists are the developer of, take over the role of a photograph in attosecond sort of spectroscopy.
So that's a very interesting and clear description, I think, of this collaboration between experimentalists and theorists that you always find, especially in modern physics, where the two really need to work together in order to to bring physics forward. So thank you for that. I'd like to back a little bit and go back to the breakthrough experiment, which I was told took place in a basement in Vienna in 2001. And if you would like to bring us back with you to that work and that moment. And I think that it was Dr. Hentschel and Professor Kienberger that were there also as graduate students at the time, if I've understood correctly.
Yes, so, I joined the institute in 1998, I think, with my master's thesis. And already at that time, there was the laboratory was full of very complicated equipment. So I remember when I came the first time to the lab, it was completely dark and only red and green lasers everywhere and huge optical setups, so optical tables full of optical components. So that was very interesting and fascinating. And so, yeah, and there were already laser systems, oscillators producing short laser pulses, femtosecond laser pulses at that time. And then amplifier systems, which were used to boost the energy of the pulses, and then different compressor systems bringing the pulse durations down. So that was already there, and then there were the experiments with high harmonic generation. So that's basically the process where these attosecond pulses are produced. And yeah, so in the first stage of my PhD work, I worked on the laser and amplifier systems, improving them, trying to get more energy into the pulses. And then in the next part, I went into these high harmonic generation experiments. So really producing those XUV radiation, starting some characterization experiments. And then in the last part, which was around 2001, then we really went for measuring those or trying to find proof for these attosecond pulses. And then I think that's also when Reinhard joined. I don't know the exact date anymore, but around that time, I guess, 2000.
Yeah, so I actually started with a completely different topic. I was working on relativistic electron acceleration with lasers. And then at some point in 2000 or so, I was asked to help out in the project of Mike Hentschel for a month, and then he would help me for a month afterwards, and my month never stopped. So it turned out that it was an extremely shall I say, demanding experiment. So one person alone could not drive this experiment. So we had to work together, and we teamed up. I mean, we were measuring for nights, days and nights. And also we were measuring basically every day, also on Saturdays and Sundays. So sometimes we made a break during the week to go on.
But they were not instructed to do so, I should say.
No,
they were not instructed to do so, right?
We were eager to do this. We knew that we have to get over this step to measure these first pulses, and that's why we were extremely motivated at that time.
Was there a Eureka moment when the actual breakthrough was clear to you?
Well, I would say it was a measurement that started at 8 in the evening and at 5 o'clock in the morning. So you maybe one can describe this a little bit. So we had two mirrors that had to be adjusted, and this was automized. So we had a potentiometer which we adjusted, and then there was a measurement of 3 minutes. Then we took all the numbers, wrote them into a lab book. Sounds like a little bit middle-aged today, right? And then we made drawings, and during the night we saw these modulations, which in the end we could identify as the measuring of the electric field by an attosecond pulse. And when we stopped at 5 o'clock in the morning, we knew that this was it. And yeah, well, we then tried to repeat it, and sometimes it did work, sometimes it did not work. It was like in this cellar, we were also not allowed to open the door because then the cold air from outside came in, and we lost track in the measurement. So it was really a demanding measurement. And after we had confirmed this measurement, we published it, and then I think record time this was published at that time.
Did you keep the notebook?
We are searching for it. We kept.
So I have the lab book of the year 2000, and we already saw some measurements, but they were not perfect yet. So we knew that we had to go through a whole trace, and we mostly lost track over the time. But of course, we had a lab book, and I'm sure we will find it again.
Absolutely,
right?
absolutely.
I trust in you, Ferenc.
So Professor Krausz, what is this thing working at night? Why was it so important that your PhD students stayed up all night working in a cellar?
Well, I think this was not very special to our experiments, at least in laser science, but probably also in other fields of experimental physics. During the day, there's just too much perturbation around, and whenever a new discovery is on the horizon, this by definition means that the measuring instruments are operating at their absolute limits, right? Just about to possibly see something. And that means that this can only happen, if at all, if everything is completely dark and quiet and so on, just as Reinhard mentioned before. And of course, these conditions can be best provided during night.
Yes.
Also, one might add, I mean, the laser system, as we heard already, it was very complicated. So there were a lot of components, an oscillator. It's a whole chain of contraptions and pump lasers, vacuum pumps, which are all devices that need some time to warm up and get into proper operation. So simply the time when we switched on all the systems until the system was stable and aligned and everything really prepared to start the real measurement, that took basically at least the whole afternoon. Right. And so then we were basically ready to do the real experiment. Another reason why we typically started to measure when all the other guys went home. Or
and my next question is, how does this research connect to the research of the other two physics laureates this year, Pierre Agostini and Anne Lullier?
Well, I would say the research of Anne laid the foundation with the discovery of the high-order harmonics, which was the process that eventually produced, from which the attosecond flashes of light eventually emerged. Anne's group and actually all other groups at that time have been using kind of conventional femtosecond pulses, in a sense that they consisted of quite a few, typically 10, 20, 30 wave cycles, oscillation cycles. Correspondingly, what theory predicted that this process of higher harmonic generation should yield was a so-called train of attosecond pulses, where in each half cycle of the oscillating electric field of the driver laser, an attosecond burst is supposed to emerge from this interaction that would focus this laser light into a gas of atoms. And basically, we see the higher harmonics. If we do everything properly, then they are superimposed on each other in such a way that the result is such a train of attosecond pulses. And that's actually what Pierre Agostini indeed managed to prove in an experiment, that indeed the temporal structure of this high-order harmonic radiation, when being driven with such a multi-cycle laser pulse, is indeed a train of attosecond pulses. This was the Paris experiment back in 2001. Parallel to all these developments, we were working on pushing the limits of femtosecond technology with various technologies. On the one hand, and this already touches on other point that we may going a bit deeper into later on, collaborations. We actually realized that our colleagues at the Politecnico Milano invented a wonderful technique to actually make short pulses even shorter by sending them through a gas field hollow waveguide, and due to nonlinear interaction, broaden the spectrum of the pulses, basically create a precondition for shorter pulses. But broadening the spectrum is not yet enough. We also have to do something else. We have to make sure that different frequency components are lined up properly, and this was done by another invention which came from Budapest. Another similarly ingenious invention, and these have been the so-called chirped multi-layer mirrors. And these two inventions together, we combined them in Vienna. So we brought the chirp mirrors with the colleagues, of course, from Budapest. We got the hollow fiber from Milano, coming, of course, again with the collaborators from Milano, and we put this together and actually managed for the first time in the world generate really, really powerful pulses which were consisting just essentially from a single oscillation cycle. So now the rest is simple, right? I mean, if you do the same thing, this high harmonic generation, this time just with a single cycle, then you are expected to replace your train of attosecond pulses with a single isolated burst. This we knew, these conditions we had back in '97 in our lab. And basically we generated these high harmonics and we measured the spectrum with conventional instrumentation, but we had no way, no method in our hand to actually prove that indeed this radiation is that short that is coming out. And here again, international collaboration. We were inspired by an ingenious scientist across the ocean, Paul Corcombe at the University of Ottawa, Steschi Institute of Molecular Science in Ottawa, who came up with the idea of the so-called light field-driven streak camera, and it looked like our experimental conditions are just ideal to implement that idea. And that's what we started working on around the end of the 90s. Took a couple of years. And these heroes here to get this operational, and 2001 it started operating, the first light field-driven streak camera. And it has proven that from the interaction, indeed, as we realize it, a single isolated flash of sub-femtosecond duration emerges.
So maybe I
Yes,
would
please.
like to add something for general understanding, because the reason why this high order harmonic generation was so important or was necessary that we could enter the attosecond regime is that if you have a light pulse with the electric field oscillating, you need at least one oscillation cycle of the electric field such that the pulse can propagate. And so the wavelength that you have defines the shortest possible pulse duration of a pulse. And in wavelengths that are common in lasers in the visible or near infrared region, then you are at a few femtoseconds. And that's why in order to be able to make shorter pulses, you have to go to shorter wavelengths. So from red to the visible whole ultraviolet, extreme ultraviolet, or even the X-rays. And this was the importance of Anlilier's finding, that one gets a frequency conversion from conventional lasers to the extreme ultraviolets, where you can make these short pulses. And that's why it was important for us to use this method. And then with, under special conditions of really few cycle pulses, just a bit more than one cycle as the laser driver, one could go to measure single isolated attosecond pulses. So this is maybe the understanding why harmonic generation is so important.
And would it be correct to say that once Anne Lullier had laid the groundwork, in a sense, yourselves and Pierre Agostini had different approaches to creating these train of attosecond pulses, so that there were two different parallel methods being developed?
Yes, basically right. For the measurement of the attosecond pulse train, a completely different method was used. Actually, the experimental setting was quite similar at first look, but the concept was different. It was closer to a frequency domain measurement. It was not so directly visible in the time domain immediately that the structure is there. Was some calculation necessary to convert the information that we acquired in the frequency domain into the time domain, and that's how one has seen that indeed that's the result. As opposed to that, in our case, we saw, as Professor Kienberger just mentioned and described, that very magic night, as actually the measurement was performed, we have seen that the attosecond pulses must be there, because we have seen as we delayed the attosecond XUV pulse with respect to the laser pulse, we have seen in our measuring instrument this modulation. And this can only be resolved if the kind of exposure time is shorter than this half oscillation period. And the half oscillation period was 1 femtosecond, right? So it was obvious that actually the camera exposure time, the XUV pulse, this high harmonic pulse, must be shorter than this half oscillation period. It was visible during the performance of the experiment. This is a true time domain experiment, and afterwards with these kind of tools, the isolated attosecond pulse and this single cycle light wave, you can do therefore direct time resolved attosecond spectroscopy.
And just to remind the audience, so the femtosecond, it's a millionth of a billionth of a second, and the attosecond is a billionth of a second. So it's
right.
It's in your world, it's the femtosecond is very slow, but in any other world,
yes,
it would be.
But let me add that we had to pay a very high price for this beautiful high order harmonics, namely a very complex vacuum system, because these high order harmonics are in the extreme ultraviolet, which is heavily absorbed in air. So within a few millimeters, it would be swallowed by the air molecules, and nothing is left over for any application. So one had to use actually a vacuum system, and it was obvious that it's a beautiful tool for doing scientific experiments, but this is definitely not a tool for moving towards real world applications. For that purpose, we need to make attosecond technology simpler. And that happened actually in the second decade of the new millennium.
So we've talked about the importance of collaboration. You described it very, very well, how you needed to bring in different expertise from different labs around the world and Europe. But I also have a question concerning competition. Part of spending your nights in that cellar, was that also knowing that other groups, like Pierre Agostini's, were on the same, working towards the same goal? How important is competition in spurring science onwards, would you say?
Well, yeah, I mean, I would say we knew that others were also on the way to measure attosecond pulses, but most of them were concentrated on attosecond pulse trains. So I think we were basically the only group that was able to do this measurement on single isolated attosecond pulses. So I was not extremely nervous, to be honest. So we were confident that we would be the ones to be able to do that. So you know about the others.
If it's doable. If it's doable,
yeah.
right?
If it's doable, then I think because we were pursuing this special way to go to these single isolated pulses, and yeah.
So I'd like to bring the theoretist into this discussion as well, the developer of the images, Professor Yakovlev. So. In this we're talking about collaboration now. We heard a lot about collaboration from different experimental techniques, but what do you see as the greatest importance of joining an experimental group as a theorist to?
In the framework of collaboration, or just theory and experiment?
Yeah, I mean, it is a collaboration, isn't it?
Work with theory and experiment.
Yeah.
Oh, that's how science works. That's common. It's nothing special to attosecond physics. So there is experimental data, and it has to be understood. And if it's something really, really new, it's not just putting together a model and demonstrating that the experimental curve and the theoretical curve are close to each other. Frequently the challenge is to build up a concept, a physical model that explains the measurements and says that's how nature really works, that's how it's supposed to work. Think about that. And each such insight inspires new ideas and experiments, and it goes to and fro. It's really synergetic collaboration that I've enjoyed throughout my career, and that's how it works.
It must be a lot also about, you're a physicist, but I say chemistry, that the exchange within the group of actually seeing what kind of theory do we need to develop in order to understand and develop this experiment. So the kind of chemistry between the scientists, is that when you choose your collaborators, is that important? Or is it only maths?
No, I mean, here this is kind of an in-house collaboration because Vlad was in the same group. But sometimes you have to approach other groups and you choose them from the topics of their research. And you say, this particular group could be the one that could explain what I have measured or model what I have measured. So you're looking at theoreticians, you know what they are working on, what methods they are using, and then you approach them and give them a call and say, look, we have some measurement, we would like to understand what's going on there, could you help us?
And I gave already one concrete example regarding the basic concept, but of course there have been quite a few more who actually contributed. For instance, the group of Professor Heinzmann, those days at the University of Bielefeld, they have actually constructed the time-of-flight spectrometer, which was a very essential key instrument in this whole apparatus. Also the actual mirrors, which were focusing these XUV light, as well as the laser pulse onto the same target where the actual experiment took place. So they have contributed truly key parts of the experiment. And later on, we also started collaborations with great theory groups. Actually, Professor Joachim Burgdorfer from Vienna have been our long-term collaboration partner, and we could continue here certainly the list of collaborators. So that's as Professor Yakovlev said, that's how actually science can efficiently work, that we define a problem and then we try to assess what part of the problem we may be able to deal with ourselves based on our know-how, on our expertise, and then we realize there is quite some missing parts and then look around who could bring in those missing parts with their know-how.
We'll soon... I'm sorry.
Maybe I just wanted to add something to the role of theoreticians, because it sounded a bit like we are doing the experiments, we deliver the raw data, and the theoreticians process the data and deliver the final result. But it's actually many times theoreticians bring up either ideas for experiments or first ideas, what could be possible to do, or during the experiment they make suggestions, okay, this and this doesn't work, well, I can calculate this, maybe if you do this differently it would work better. So they make suggestions how to get a non-working experiment to work. So it's not just the data processing, it's more than that.
Sure,
yeah, way more than that.
Thanks.
So I'm soon going to open the floor for questions from the audience. But first, Professor Krausz, I would like to ask you, you came to Germany to do science from Hungary via Vienna. So I have a question to you. What is special about doing science in Germany? Is there anything that is particular about the way German science functions that you would like to comment on?
Well, I think not the general way that would be different, but there are just locations where there is a particular concentration on know-how and environment, which is particularly kind of fertilizing and supportive. And Munich is such a location where there is really a unique range of expertise around, not just in laser science and related fields, but way broader than that. And I think this was, for me, a major reason why I thought, wow, that's perhaps the right time to do this move. Not because I was not extremely happy and thankful to what I received in Vienna, and I really have to say that probably these have been my most beautiful years, actually not just professionally, but also privately. My two beautiful daughters were born there. But I thought that these wonderful tools that we have, these heroes here, have brought to life in Vienna, maybe we have a better chance to bring these tools and technologies to fruition in Munich with the joint forces of the Max Planck Society, in my case via the Max Planck Institute of Quantum Optics and the Ludwig Maximilian University, two leading research organizations in Germany. And I think, in retrospect, I think this was a good decision, because I really, really enjoyed, just as in Vienna before, every moment of working in this environment. It's invaluable.
And the Max Planck Institute is, of course, a particular aspect of German science. Would you like to say anything about how that fits into the...
Yeah, I mean, the most beautiful thing about the Max Planck Institute, Max Planck Society, is that we are so free. And on one hand, and also we have a financial framework which allows us to actually put ideas extremely quickly in practice. Unfortunately, at universities, we do not have this kind of freedom. I mean, of course, we are free to think there as well, but and free to develop ideas. But if we want to do these ideas in practice, we have to write a grant proposal and wait and wait and wait. And if we are lucky enough and good enough in writing grant proposals, then maybe half a year later, 8 or 10 months later, we will get the resources to actually start working. This 6, 8 or 10 months are just not there. Within a Max Planck Institute, we can start working on that next day, and that's truly unique. And I think many of us, many, actually a large part of the scientific community very much envy us for that, for this kind of freedom. Not just free to think, but also be very quick to realize ideas.
I've certainly heard many Swedish scientists being jealous of the Max Planck Gesellschaft setup. So I'd like to open the floor now to questions from the audience. Yes, please.
I'm Professor Mohammed Bornen. I'm from Stockholm University in quantum optics, and I'm also a member of the Swedish Academy of Science. First, I'd like to congratulate you, and I want to. This was my question coming to the directors and the researchers at Max Planck Institute have shown excellency and breakthrough results, you know, and through the number of awarded in Nobel Prize, right? And then through, as you say it, exactly through the freedom and also this long-term perspective and financing and stabilities. And my question to you, are these specific to Germany, or one could other country in Europe, you know, could adopt such model of institutes?
I guess potentially, of course. Why couldn't? But certainly, there is also some need for a economic strength to maintain an organization such as the Max Planck Society. But on the other hand, I wouldn't see any reason why correspondingly scaled smaller Max Planck societies couldn't work in other European countries. Absolutely. I mean, just as the European Research Council was clever enough to kind of copy the DFG, right, in terms of the rules and operations, there is no reason why the good practices that are tried and tested and the results are being proven by the series of Nobel Prizes just also over the past 5 years or so, why this concept could not be copied in other countries. Sure, I would encourage any European country to look into that. Absolutely.
Could you see it happening within the auspices of the European Union?
Potentially, yes, but I think each and every member country could do it themselves. I think what is important that probably every country has to realize. I guess even Germany, by the way, with all its economic power, that it is almost impossible to fund science in absolutely all areas at such a level that particular part can actually be at the absolute top of the world. One has to identify those areas and kind of focus resources cleverly. And the more clever this is being done by the corresponding organization, of course, with the participation of the scientists, I think the most successful science will be in the respective country.
Yes, please.
I'm Claes Fallander. I'm a professor of physics at Lund University and also a member of the Royal Swedish Academy of Sciences. I just wanted to continue on that subject a little bit, the Max Planck Institute, because we visited Vienna a few weeks ago, and we learned that the Austrian Academy of Sciences, there are some independent institutions that are coupled to the academy, and I got the impression that those institutes somehow worked in the same manner as the Max Planck Institute. Maybe you can comment on that.
Well, I'm aware of, I think, for instance, the ICOCE, which is an institute of the Academy of Sciences. Although to be honest, I'm not very involved in the how they are financed. So as far as I know, they need to write proposals as well. I suppose there is some basic budget. I don't know how it compares to the Max Planck Gesellschaft financing scheme. So.
Yes, that's a question.
So my name is Tunda Philip. I'm also a member of the Royal Swedish Academy of Sciences, and I have a question for Ferenc Krausz. What is the next scientific goal? Because, you know, some people get the Nobel Prize twice, Marie Curie. So what is your vision? I was so impressed that you had this goal and perseverance to not be distracted and pursue it. So maybe you have another.
Oh yes, absolutely. It has nothing to do with the Nobel Prize, but of course there is another goal, and this is to actually, well, what the current chair of the Nobel Prize Committee for Physics said so beautifully in her statement on the very day of the announcement. Now it's really time to utilizing these tools to prove that these tools can indeed be useful, so useful that each one of us eventually will see the consequences. That's what we are working on, and it's a medical application.
You won't tell us anything
more
about
yes, of
the
course. If I have time, yes, I just try to keep answers short. But of course, I just wanted to provoke your question. Thank you. Now I am encouraged. Yes. So the idea was actually it also demonstrates how little we can actually foresee when we create a new tool, a new technique, a new kind of method. How little we can possibly foresee what this is going to be good for, because this particular application that I tell you a few words about was absolutely unforeseeable at a time when we generated and measured these attosecond pulses. And it relates to the capability that with the tools we have developed for actually capturing the motion of electrons, we can also sample the oscillations of the electric field of light. As Professor Kienberger said, that actually basically came to light already in the first experiment, these oscillations. So this is inherent in attosecond technology, that we can capture, we can not just measure how the intensity of a light pulse varies, which femtosecond technology could do over a couple of decades before, but we can actually look inside this intensity and see how the electric field oscillates. And this was actually the opening of the door. This opened the door to this particular application, where we illuminate samples of human blood plasma with an extremely short, again, ideally a single cycle infrared pulse. That means that the wavelength is slightly longer than the pulses have been used for attosecond pulse duration. Not very much, slightly. Few femtosecond is a period, 5 to 10 femtosecond, with just a single cycle, and bring the molecules into vibration. The vibrating molecules do radiate infrared waves at many different frequencies where they like to vibrate. And at which frequency they like to vibrate is characteristic of that particular molecule. So if we could, basically in this signal that it comes out, this sum of infrared waves from this sample containing all these vibrating molecules, like a tuning fork after being hit. These contain a great deal of information about the molecular composition of a sample. Whenever this molecular composition changes due to some emerging abnormality, this signal changes. And we are after these changes. With attosecond technology, since we can capture very, very precisely and sensitively this oscillating molecular signal, we can very sensitively measure these changes. And then we try to see whether these changes are in a robust correlation with a certain condition. And as you can guess, for
you mean a certain medical condition?
Certain medical condition, a certain physiological condition, a certain disease, if you like, right? And as you can guess, for this we need big collaborations with medicine, and that's what we started building up in the middle of the past decade, around 2015 or so. It took us about 3 years to actually collect all the ethical approvals and so on, to even start collecting samples, and could, fortunately enough, get quite a few chiefs of clinics on board, who actually then decided that they join in with their teams and help us collecting those samples in the first few years from different from patients of different types of cancer. In the first place, lung, prostate, bladder, and breast cancer. And we have then collected enough samples, particularly in lung cancer, so that we could start really doing detailed analysis, measure these fingerprints from the samples from cancer patients and the fingerprints from equally importantly, the healthy references, because we always need a comparison. So we always needed to collect a sufficient or similar number of samples also from healthy individuals not carrying the disease. And we indeed found out that we do see very, very pronounced signatures of the disease in those signals. And meanwhile, we are quite encouraged by the fact that it seems like we can see strong signals even in a stage before actually the cancer starts to spread and metastasize. So basically stage 3 and even below that, which is extremely important because currently 50% of all lung cancer diagnoses are being made at stage 4 in the world. This means 1 million stage 4 diagnoses worldwide, year by year. 1 million people die of this, not because there are no therapies around. There is a lot of really efficient therapies around. But these therapies cannot do anything much at that stage. They could do a lot at stage 3, 2, and 1. So that's why it would be so extremely important to capture this disease at an earlier stage. And this, of course, applies not only to this disease, but to a number of other chronic diseases.
So it's a very sensitive measurement of the molecular composition of the blood that will tell us at a very early stage of a cancer.
Changes of molecular. We are always interested in changes, right? Yeah.
So can you envisage this actually, that you could actually scan for in blood samples in a simple way for different sorts of cancers in the future using this kind of
Well,
technology?
that's a long way. That's a long way. But we have meanwhile collected samples of 8 different types of cancer, and for all 8 different types of cancer, actually, we do see disease-induced signals, very clear signatures. So obviously the method is, so also, first of all these cancers do change the molecular composition of blood significantly, which is, by the way, not necessarily some new molecules coming from the actual tumor. We don't believe we could see them if they come, because they would have a very low concentration, but it's much more like how the whole organism responds to the presence of the tumor in the body. That changes basically the concentration of the molecules, which are always there, but now under these new conditions where the tumor is in the body, these concentration just move to a new equilibrium value. And the bigger these changes, the bigger the change also in the signal that we see.
And this was nothing you imagined when you were in that cellar looking for the attosecond train pulses?
For sure not for us, but I'm just wondering, do you think that any of you in our place could have foreseen this?
Do we have any more questions? Yes, Ulf Danielsson.
Yes, I'm Ulf Danielsson, Uppsala University. I'm a secretary of the Nobel Committee of Physics. If you were 40 years younger and could start all over again, which field would you pick? You cannot say attoseconds again. It has to be something completely new.
Thank you for the question. Great question. I guess my second choice would be astrophysics. I'm just fascinated about these things like dark energy, dark mass, and all the information that our colleagues in that area can collect, basically from outer space in those also extremely weak signals. So there's quite some similar, and they are also using also lasers, and of course I should mention, and are also dealing with extremely weak signals. It's just incredible. And then they can say, okay, what did happen something like 13 billion years ago, right? And because this signal is just about to tell us something, what happened at that time is just for me like, wow. It's really exciting. So probably this would be in strong competition with ultra short pulse laser physics.
So we have time for 1 or 2 more questions. Yes, please.
Yes, hello. My name is Elmer. I'm with a large telecom company from Sweden. We have many researchers, and I think my question would be, how did you cope with going all the way towards this success? Because we know that in research, a lot of work is not directly leading to success in the very first step, so to say. So what was your kind of way to stay perseverant, and also your colleagues over all of the years to reach this target? I think Einstein once said that a lot of what we do has to go basically on the shelf. We have to revisit it over and over again. So how did you manage? How did your group manage?
Before you answer that question, I just want to address the people following us online, because the live stream will end in 1 minute and 45 seconds. But for the audience here in Stockholm, please feel free to develop your answer. But
okay, I'll try to transport the most important part in the remaining 90 seconds. So I think everything starts with the right question. I used to say this quite a few times, to find a question that really fascinates you, where you are absolutely convinced that if you find the answer, this can be something big, something important. This is one thing. This furnishes you with the necessary amount of determination and resilience, being able to overcome also difficult periods, which are repeatedly happen very frequently. I'm sure you can agree, and also stay focused, because there is so much chance to distraction. There are always something new is come. Oh, could we look at that? Could we look at that? And then always coming back. If we look at that and spend the next 2 weeks for that, does this bring us closer to answering that big question? And if the answer is yes, then no. We don't have even the 2 weeks for that, but just go ahead and go on. And perhaps the last thing, to learn how to deal with failures, which is the usual business, right? Working at the top. And it's really at the forefront, failure after failure. Not feel it as a failure, but as a source of new knowledge and the chance to develop new ideas.
And with that, we say thank you to those following us online. Thank you very much, panelists,
thank you.
Professor Krausz. Please feel free to continue for our audience here in Stockholm.
I think the main thing is done. Next question.
So I think we do have time for some more questions here in the room. So please feel free.
Yes, so I'm Rune Toftgård from the Karolinska Institute here in Stockholm. So I think your research here is a beautiful example of how new technology allows us to address new questions. And I guess this with the cancer screening is a new question, things that can be addressed in this case. So I have basically 2 questions around that. And that is, A, how early do you think you actually will be able to do this, to apply this screening? And secondly, are you also thinking about actually starting prospective studies to evaluate the potential clinical impact of such a screening?
What a wonderful question. This is the right question. Thank you. Yes, actually, this is exactly in the focus of our activities after having seen that basically the signal is there, which is now absolutely clear. Not only for lung cancer, by the way, but we have seen robust signals also for cardiovascular and metabolic disorders meanwhile. So actually these 3 groups, cancer, cardiovascular and metabolic disorders, these 3 types of diseases are responsible for 75% of all deaths on this planet. Right? So if one could come up with a method with which one can capture these diseases at their early stage, this could save many, many millions of lives year by year. And that's exactly what is our goal, the remaining goal, and actually a mandate given us from the Royal Swedish Academy by the decision to prove that they were right, that this field indeed deserves this because it will spawn something important, and we are trying to work on this important, and I'm in the really extraordinarily fortunate and pleasant position that I'm allowed to pursue this very goal also to a large extent in my home country in Hungary, thanks to a very sizable and very, very significant support of the Hungarian government, which allowed us to start actually to roll out a so-called longitudinal follow-up study back in 2019. Actually, it was delayed by the pandemic, so it could start only a year later. But meanwhile, we have recruited more than 10,000 individuals. Initially, they are supposed to be healthy, and we are just about to recruit another 5,000 so-called high-risk individuals, actually high risk for one of these 3 groups of chronic conditions. Actually, if they are high risk for one, usually they are high risk also for the other 2. And there will be in total then 15,000 individuals, which we plan to follow up over 10 years at minimum, hopefully longer, but at least 10 years, with a yearly blood draw. Initially, actually, even more frequently than once a year, but later on just once a year. And unfortunately for the individuals, but fortunately for scientific progress, a certain fraction of these individuals will contract one of these 3 diseases. And we even know the number pretty precisely, the incidence. It's going to be around 100, 150 lung cancer, around 200, 300 cardiovascular disorders, and 400, 500 metabolic disorders, primarily diabetes type 2, of course. And the big advantage of such a longitudinal study is that we will have the samples at each stage of the disease. One has to wait until it can be eventually diagnosed, because unfortunately contemporary medicine is obviously not in a position to diagnose these diseases at the very beginning. Then we would not have to do this research at all. But in many cases, only when the symptoms are there. And these are years after the actual initial stage is about to emerge. And we have to wait those many years until the diagnosis is there, and then we can go back and reanalyze, particularly those samples, and then try to establish a correlation in the change of the signal and this particular condition. And this would be the kind of validation of the method, validation that this method is able to detect this particular disease at such and such early condition, early stage.
So I'm sure that there are many more questions in the audience, but I think that perhaps we should save those to the more informal gathering after this. I would like to thank you all, the whole panel, Professor Krausz, and also the audience for your questions and participation, and give back the floor to the ambassador.
Thank you very much.
Thank you.
Thank you very much. It was super interesting, and I looked at my watch, I must admit, because I said that your research had also an effect on medical diagnostics, and I was really waiting for that subject, because I think we all care very much about it. We all have family members who suffer from cancer or other diseases, and it's so important